The last lecture, I worked out the energy levels for a charged particle moving in a uniform magnetic field, and I've summarized some of the calculations here on the board. The main result was the energy levels, which depend on two quantum numbers, n, which is the Landau quantum number, and then p3, which is the momentum parallel to the magnetic field. You know, the particle moves as a free particle in that direction. The Landau level corresponds to a harmonic oscillator with energy input to half h bar omega. Interestingly enough, the Q and the P of the harmonic oscillator are basically the x and y components of the velocity, which don't commute with each other. So the harmonic oscillator itself is really just Vx squared plus Vy squared times m over 2 as the kinetic energy. This is the quantized values of the perpendicular kinetic energy of the particle. In fact, the whole energy is kinetic energy. Anyway, that was the main result of last lecture. And in this lecture, what I'd like to do is to start by working on the not just the energy levels, but also the energy eigenfunctions. So, let me start with a little more here and get to work on that. The strategy is going to be to choose a complete set of commuting observables, a CSCO. For starters, we can take for starters, we may notice that the perpendicular Hamiltonian and the parallel Hamiltonian commute with each other. I'll have to keep lifting this up to show you the summary from last time. But the reason they do is that, you know, there's 3 degrees of freedom. One, which is basically the guiding center position, x and y, the q and the p. The 2 degree of freedom is the x and y components of velocity. And the 3 degree of freedom is the z and pz in the parallel direction. So the reason that h perp and h parallel commute with each other is that h perp only involves number 2 degree of freedom, whereas h parallel involves number 3. So they commute with each other because the commutation relations are qi pj is I h bar delta ij. So the commutators are 0 for different degrees of freedom. So the Hamiltonian is a sum of 2 terms that commute with each other, and so we can take these 2 terms, h perp and h parallel, as being 2 of our members of a complete set of commuting observables. Let's write the set like this. Now, actually, as it turns out, instead of h parallel, it's actually better to use p3, the parallel component of the momentum. This is really just a one-dimensional free particle. And the idea here is that momentum is preferable because the energy is degenerate. You know, in a free particle in one dimension, you've got 2 waves traveling in opposite directions have the same energy. That's resolved if you use the momentum as the quantum number. So allow me to do that and replace h parallel just by p3, like this. That gives us 2 commuting observables. But we need another one, and it's pretty clear that we do because the number 1 degree of freedom is not represented by h parallel and h perp. That's the x and y, the guiding center positions. So if we want to find a third observable which commutes with the first 2, it obviously can be any function of q1 and p1. Or for that matter, it could be, call it x and y. It's the same thing apart from these constants. So it's the guiding center position, some function of m. And the simplest choice is just to take it to be x. We can make it y. Let's make it x just to give it a choice. So let's take a complete set of commuting observables, and we'll take it to be x, h perp, and p3. And our strategy then will be to find a set of simultaneous eigenfunctions of those observables. All right. So what we're going to look for then is to solve a set of equations like this. We're going to wave functions from each side x, y, and z. And we want, first of all, that x acting on this, the operator, brings out an eigenvalue we'll call x. And you can see I better distinguish the operator from the eigenvalue. So let me use my usual trick of putting hats on any operator where I think there's going to be a confusion between the operator and an eigenvalue or some other C number. So anyway, this is the eigenvalue eigenfunction equation for the operator x hat. Likewise, we'll have h perp acting on the same side. We'll bring out an e perp, perpendicular energy. And we'll have a p3 hat acting on the side. We'll bring out a p3 eigenvalue acting on the side. all the time psi. So these are three simultaneous eigenvalue equations that have to be satisfied. Now, so let's work on these. The H perp is the most complicated of all, and the P3 and X hat are simpler. So let's do the simple ones first. Let's work on P3 hat first. P3 hat is from the formula down here. It's the mass times Vz. And Vz, the velocity, is expressed in terms of the canonical momentum and the vector potential by this equation. So we'll put those together. And P3 hat then is equal to the mass times Vz. I'll put a hat on Vz. And that's the same thing as momentum Pz plus E over c times the vector potential Az, which in general depends on x, y, and z. And so this eigenvalue equation, the third eigenvalue equation, looks like this now. It becomes, replaces Pz by the operator minus IH bar dEz. We get an equation like this, minus IH bar dEz plus E over c times A sub z, which is a function of x, y, and z, acting on psi is equal to eigenvalue P3 times psi, same psi of x, y, and z. Now, what makes this equation hard to solve is the vector potential component A sub z. And so we ask ourselves, is it possible to choose a gauge? Let's try to choose a gauge now to simplify the equations. Can we choose a gauge such that Az is equal to 0? Can that be done? Well, let's write out the equations, the components of B equals del cross A. If we take the Z component, we have B, which is the same as the Z component, is at dAy with respect to x minus partial AX with respect to y. Just write out the full equations. 0, which is dx, is equal to partial AZ with respect to y minus partial AY with respect to z. And 0, which is dy, which is the third component, is equal to partial AX with respect to z minus partial AC with respect to x, just writing out the curl. Now, if AZ is equal to 0, if we provisionally guess that we can do that, then these two terms here go away. And you can see that what's left is that dAy with respect to z is equal to 0, and also dAx with respect to z is equal to 0. So these equations imply that AX is a function only of x and y now, and it also, the same is true for AY, is only a function of x and y, that AZ is equal to 0. This means, as you can see, that the entire vector potential is now independent of z. So partial of the whole vector potential with respect to z is equal to 0. This means that the vector potential is invariant under translations in the z direction. This is one of the symmetries of the magnetic field. If the magnetic field is uniform in the z direction like this, it obviously has a symmetry, a translational symmetry in the z direction. If you move it up and down, it doesn't change anything. You can also move it to the right and left or backwards and forward, and that doesn't change anything either. The magnetic field has a symmetry, translational symmetry in all three directions. It also has a rotational symmetry about the z-axis. Only about the z-axis, not about the other axes. But anyway, this magnetic field, this uniform magnetic field, has four obvious symmetries. And now one of them is reproduced in the vector potential, namely the z translational symmetry. So let's do that. Let's make this assumption. And if we do that, it cleans this up because this term goes away. And also, if we do that, then this term goes away, and we see that P3, the operator, is the same as the PZ operator. So let's just change notation now to the same thing. So let's just take P3 hat and just replace it by PZ, because that's what it is. And likewise, do the same for the eigenvalue. Replace that by PZ. So I'll take this and replace this just by PZ. And so now the equation is easy to solve, and it gives you psi of x, y, and z is equal to e to the I pz times z over h bar times an arbitrary function of x and y. Because there aren't any x and y derivatives here, this is the general solution of that equation. And so the z dependence is determined, and it turns into as you see, a plane wave in the z direction. Logical sense, the motion in the z direction is that of a free particle. All right, anyway, this takes care of the third eigenvalue equation, which is the P3 equation. Now, the next easiest one to work with is the x equation, so let's do that. I'll try to start it here, then I'll shift to another board. So the x, I'll remind you, the guiding center x is defined as the coordinate x minus Vy over omega, and Vy is given in terms of canonical momentum and vector potential by the standard formula. So in terms of operators there, this says that the guiding center operator x hat is equal to the particle position x hat minus Vy hat over omega. And that's the same thing as particle position x hat minus 1 over m omega times Py hat plus e over c ay, which we now know is a function only of x and y. And that's an expression for the x operator. I'm putting hats at everything where I want to distinguish an operator from a number. And so the equation x hat psi is equal to x psi, the eigenvalue equation, turns into the differential equation, which I can write out like this. It becomes x minus 1 over m omega, and then we've got minus I h bar d dy, that's for the Py here, plus e over c, a of x and y. And that whole thing multiplies our psi of x, y, z, and gives us eigenvalue x times psi of x, y, and z. Now, however, the psi, we've already determined, is a phase factor in the z direction times an unknown function in the x and y, of x and y variables. We're going to determine this phi function by using these other two eigenvalue conditions. And in particular, plugging in this expression for the psi at this point into the two sides of this equation. You can see there aren't any z derivatives or anything else that depends on z on either side of this equation. Thus, the phase factor, e to the IPZ over h bar, PZZ over h bar, just cancels. And so, let me get this up to another board here. So those just cancel, and it ends up being just an equation in y. Before I lift it up, I want to do one more thing. Now, having done that, there still is not exactly an easy-looking equation. And the main reason is, again, because of this vector potential here. But in addition, there's also this x over here. So before proceeding, let's ask whether we can take this vector potential and use it to cancel out that x. It's there on the other side. How do we make that happen?
That a is supposed to be ax?
That's supposed to be ax, yes, thank you. Ax, indeed. No, excuse me, it's ay. Because this is the py, which came from dy, yes. All right, so can we do that? Well, if we do, if those two terms cancel, then the x here, there's a minus sign 1 over m omega and a plus sign here. So what we have to get is a condition that says that x is equal to e over m omega c times ay. Or, obviously, ay is equal to mc over e times omega, which is ed over mc, times x. And mc's cancel, and the e's cancel. And so this leads to ay is equal to x times b, if we do that. Now, if ay is equal to x times b, then this term in the curl equation is just equal to b. So b equals b, and therefore ex dy must be equal to 0. And so the logical choice for ax is to take ax equals to 0. And if we do this, of course, these are now they are functions of x and y, and they're really only a function of x. If we do this, we now have a specific, completely determined the gauge here. And there's a pretty good choice of gauge. And you can see that the vector potential now has only a y component, and the y component depends only on x. This means that now not only is the vector potential independent of z, but it's also independent of y. So it's translationally invariant also in the y direction, both the y and the z directions. It is not, however, translationally invariant in the x direction. And it better not be, because if it were, it would have to be zero. It would have to be constant. If it were constant, then the magnetic field would be zero, and the magnetic field is not zero. So there's a moral in this, which is the vector potential can never have all the symmetries of the magnetic field. It can have some of them, but not all of them. In any case, here we've set it up so it has the y and the z translational invariance, but not the x. All right. Anyway, this has now given us a complete choice of gauge, and we can now solve this x equation. And so it's going to look like this. It's pretty easy to solve. So it's going to be, I just need to clean this stuff up here. The x and the a are going to cancel out. And the rest of it is I get an IH bar over m omega ddy from here and here. And that acts on what's going to be phi of x and y. And that's equal to capital X times phi of x and y. Capital X is the eigenvalue of the Eigencenter position operator. And this is easy to solve. It says that phi of x and y is equal to e to the minus I m omega times capital X times y divided by h bar times an arbitrary function of x. So, as you see, by taking care of the x-hat equation, we've now gotten the unknown eigenfunction down to just a one variable x. And so this still leaves us finally with just h perp. So let's now write down the h perp equation. So h perp is an operator. Is 1/2 m times dx squared plus dy squared. That's the hats on these, if you like. This is the same thing as 1/2m px plus e over cax squared plus 1/2m py plus e over cay squared. Of course, we've just decided that ax is 0, so that goes out. And px here is going to turn into minus sine h bar dpx. As far as e over cay is concerned, the ay is up here. It's x times b. So this is EB over C times x, which if I multiply and divide by the mass, turns into m omega times x. That's the particle position x. As far as the py is concerned, that's minus I h bar ddy. What this is going to act on, well, we don't need to let it act on the full function psi because the z variables don't appear anywhere in h perp, so the z phase factor will just drop out. So what we want to let it act on is a function phi. The function phi is a phase factor in y times f of x. Now, the y derivatives do appear. They appear right there. But they're going to act on this phase factor and bring down a constant. As you can see, the ddy is going to be minus our h bar times, you see here. This is, in other words, going to turn into a constant factor, which is going to be m omega times capital X, just a multiplication by it, and I think it's with a minus sign, minus m omega capital X. All right. And so after that's been done, then there's going to be a common phase on the equation h perp phi is equal to e perp phi. This is the equation we want to solve. There's a common phase factor. This y-dependent phase factor is on both sides, and we can cancel that. And so what's left over when we clean all this up is this. It's minus h bar squared over 2m times b squared dx squared. It's an equation just in the unknown function f, you see. Then what we get is m omega squared over 2 times x minus capital X squared. This all acts on f of x. And gives us e perp f of x. Now, this equation is the eigenvalue equation for a one-dimensional harmonic oscillator. You can see there's a one-dimensional Schrödinger equation. Here's the kinetic energy. Here's the potential energy, frequency omega. The only thing that's a little bit funny about it is the origin has been shifted from x equals 0 over to x equals capital X, which is the eigenvalue of the guiding center operator. And so we can write down the energies in the solute and the eigenfunctions right away. The energies E perp are going to be equal to n plus a half h bar omega. That's something we knew already. And the energy eigenfunctions f of x are going to be equal to what we call the harmonic oscillator eigenfunctions. Just use it in. This is the usual Hermite polynomials times exponentials, but it's evaluated at the shifting position x minus x. And so we can now put the whole solution together, and we have psi, the wave function, which is characterized by the quantum numbers capital X, Landau quantum number n, momentum in the z direction, which is a function of x, y, and z, is equal to e to the I pzz over h bar for the z direction minus I m omega capital X times y over h bar for the y direction times un of x minus capital X for the x variable, and that's the solution. So those are the wave functions. These are the simultaneous eigenfunctions of these three commuting operators, which we chose as a complete set. And because the Hamiltonian is a function of those operators, in particular just the last two of them, the energies, the total energies are the parallel plus the perpendicular energies. Yes?
Our argument for why we needed a third complete set of commuting and circular thing was that we had still we still had x and y, the initial position.
Yes.
But we chose x and not y, so don't you still have another degree of freedom that's not represented?
Well, this system has 3 degrees of freedom. You could see that in the original x, y, and z, which were just the coordinates of the particle. But then we also transformed them to these q's, and there was 3 QP pairs. It's the same number of degrees of freedom. But in the Hamiltonian, there's only 2 degrees of freedom that appear, the number 2 and the number 3 degree of freedom. The guiding center positions x and y don't appear, and that's because the energy doesn't depend on those. It doesn't depend where in the plane you put the circle. So in order to find an eigenfunction, you need to have a third. We need to have a third operator who commutes with the first two, and it has to be a function of the guiding center variables, because the other two take care of degrees of freedom number 2 and 3, and guiding center variables are number 1. Does that make sense?
Yeah, I think so.
Yeah. Okay. However, there was a lot of arbitrariness in the choice of this operator. It could have been any function of the number 1 variables. It could have been y, it could have been some function of x and y, and it still would have commuted with the remaining 2. Now, this is a way of saying that there's lots of ways of writing down energy eigenfunctions that have the same energy eigenvalue. The energy eigenvalue depends only on the last 2 quantum numbers, the n and the pz. So this is a way of saying this is a highly degenerate system for given energies. There's many different ways of writing down energy eigenfunctions. The reason it's so degenerate is because it's highly symmetric. If you include physical effects to break the symmetry, realistic magnetic fields don't go on forever in x and y. They have to end somewhere. In a solid, there's going to be an end to the solid, or there's also going to be potentials, electric potentials or something, and that'll break the symmetry. And then the Hamiltonian will depend on x and y, and that'll change things. But anyway, this is the simplified model. Okay, if we take let's take this wave function and sketch it to see what it looks like and try to get some ideas what it means. If I notice the z and the y dependence are just phase factors, so if you square them, they drop out, then all that's left is this harmonic oscillator eigenfunction. If we plot this in the xy plane and kind of ignore the z direction, let me put in a dotted line here for where the particle position is equal to the guiding center position. And let's also take n equals 0, which is the ground state of the Landau motion. Then un of x, then un is Gaussian, but it's going to be centered on it at x equals x. So you get a Gaussian that looks like this, except it extends out in the y direction. It continues everywhere in the y. If I include the z direction, it would be a kind of a Gaussian wall. It would be out here like this. But just in the xy plane, it's like a Gaussian mountain range, which is centered at x equals x. Now, this doesn't look at all like classical motion. Classical motion is a circle in the xy plane situated somewhere, like this. And what's the relationship between this energy eigenfunction and this classical? You might have expected the quantum wave function to be concentrated in the circle, something of that sort. But it doesn't look like that. Why is that? The reason is that we made this an eigenfunction of the operator x hat, the guiding center position. But the guiding center y position does not commute with x. In fact, they're like a q and a p apart from the scaling factor, or an x and a p. And so by constructing a state in which the value of x hat, of the observable x, is known precisely, it means that the value of the corresponding y observable is completely unknown. And that's why it has to stretch out to infinity, plus or minus infinity in the y direction. It's the uncertainty principle is forcing this on us. If we had chosen y, capital Y, guiding center y as the, instead of x, as the first observable, then we would have gotten a mountain range going in the other direction. Because then y would have been known, but x would be completely unknown. There's a homework problem in which you don't use either y or x, but you use angular momentum. And if you do that, you find the wave function is rotationally invariant around the origin. It still doesn't look like the classical motion because the circle in the classical motion doesn't have to be in the origin; it can be anywhere in the point. But anyway, at least it doesn't go to infinity. So anyway, these are all aspects of this problem. There are ways of constructing energy eigenfunctions that do look like the classical motion, but I don't think I want to go into it. Here's another curious thing about this problem, is that the xy plane, if I talk about the particle coordinates x and y, of course it's just an ordinary configuration space, and the x and y variables commute so they can be measured simultaneously. If, however, we talk about the guiding center xy plane, those are operators that don't commute. And in fact, the commutator is IH bar times a constant, so they look like an x and a p. In other words, the guiding center xy plane is really more like a phase space than it is like a configuration space. And by the way, the same thing is true for the Vx and Vy variables, which don't commute either. They're like another phase space in a different dimension. In fact, the classical orbit is a circle in velocity space. This is actually like the circular orbit of a harmonic oscillator in phase space in the classical picture. Well, in any case, to go back to the guiding center variables x and y, it's like in some respects, it's like a phase space. There's one thing we know about a phase space, which is that there's a concept of a Planck cell. A Planck cell is a cell that has an area which is equal to 2 pi h bar, and it's the area that supports a single quantum state. This is a rough semi-classical rule. Well, the x and y variables aren't quite q's and p's. There's one of the root m omega involved in them. So a Planck cell in the guiding center plane is going to be a cell in which delta q1 times delta q2, that's the phase space area, is equal to 2 pi h bar. So let's talk about Planck cells. This would be the condition for it. However, according to this formula here, delta q and delta p are square root of m omega times delta x and delta y. So this is the same thing as m omega times delta x delta y. That's the same thing as m omega is equal to eb over c, delta x delta y. And b times delta x delta y is the magnetic flux through the area of the xy plane. And so what we find is the flux through a single Planck cell, B delta x delta y, is equal to 2 pi h bar over here times c over e, which is more usually written this way, it's hc over e. hc over e is a unit of magnetic flux, and it's called the flux quantum. And this is actually an important concept in various condensed matter applications, quantum Hall effect and so on, where you have not just one particle, but electrons, you've got lots of them. in magnetic fields. And the quantum states, the ground state, the Landau, for example, fills up the area with one state per Planck cell. But the Planck cell is an area of the xy plane that it captures a single flux quantum of magnetic flux, which is hc over d. Anyway, it's a very common concept. The terminology is a little bit bad because the magnetic flux is not quantized. This is just merely a natural unit of magnetic flux that emerges in quantum problems involving magnetic fields. But magnetic flux can take on any value whatsoever. Anyway, that's the meaning of the flux quantum, hc over d. Okay. Now, that's all I want to say about the charged particle in a uniform magnetic field, and I'd like to turn to another problem involving magnetic fields, which I guess I'll do here. And this is the Aharonov-Bohm effect, which is interesting because it challenges our understanding of the role of magnetic vector potentials in quantum mechanics. The Aharonov-Bohm effect, AD effect, dates from about 1961. It's sort of surprising nobody thought of this earlier. In a sense, there's nothing much to it. It's just solving the Schrodinger. Nobody invents a new Schrodinger equation or any new physics. It's just solving the Schrodinger equation in some standard way. But the results were surprising to some people anyway. Anyway, the situation involved is that of a charged particle moving in the field of a long, thin solenoid, or a long solenoid. A long solenoid is a standard problem in electromagnetic theory, so I assume you've seen it already. Let's take the solenoid looking like this. It actually is supposed, and ideally extends to infinity in both directions. Let's take the z direction as pointing up and put coordinates x and y on this. I'll also use cylindrical coordinates when it's convenient. This is rho, phi, and z, where rho is the radius in the xy plane, square root of x squared plus y squared. In any case, the solenoid is supposed to have a current sheet, singular current sheet, flowing in the azimuthal direction around the solenoid. And the result is if you get a magnetic field in the interior of the solenoid, constant uniform magnetic field, with zero magnetic field outside. So the magnetic field is equal to, let's just say magnitude B times Z hat, if the radius is less than the radius of the solenoid. Let's call that A as the radius of the solenoid. In fact, allow me to make another picture to look at this from above. We look at the solenoid from above, so in the xy plane, I'll draw the solenoid somewhat larger now. Let's say the radius is A, like this. So if you're inside, the magnetic field is constant. If you're outside, the magnetic field is zero. Now, in classical mechanics, a charged particle moving in the exterior region of the solenoid would not feel the solenoid at all, because there's no magnetic field there, so there's no force in the particle. Charged particles move in straight line trajectories. What's interesting is that there is an effect in quantum mechanics, as we'll see in just a moment. To look at the quantum mechanics, of course, we're going to need a vector potential because that's what appears in the Schrodinger equation. So let's find a vector potential for this magnetic field. We'll do this in this manner. It turns out that you can find a vector potential which is purely in the phi direction. And we get the vector potential by doing an integral around a closed loop at some radius around the solenoid. So let's integrate around some loop of A dot dl. And that's equal to the radius, the circumference of the loop, which is 2 pi rho times A phi. However, by Stokes' theorem, this is also equal to the magnetic flux. It's the integral of B dot dA over the enclosed surface. And that's the same as the magnetic flux, which is enclosed by the loop. Well, the magnetic flux enclosed by the loop depends on whether the loop is inside the solenoid or whether it's outside. These dotted lines are two examples of loops we're going to think about here, like this, like this. If the loop is inside the solenoid, then it picks up the flux which is inside the loop. So in that case, what we get is the area of the loop, which is pi rho squared times the magnetic field. This is the case of rho is less than A. And if the loop is outside the solenoid, then we pick up the magnetic flux from the entire solenoid of radius A, but nothing beyond that because there's no magnetic field beyond that. So in this case, it just turns into pi A squared times B for rho greater than A. And so dividing by 2 pi rho, we can solve the vector potential and find A phi is equal to B over 2 times rho if rho is less than A, and B over 2 times A squared over rho if rho is greater than A. And so we can make a plot. It's a function of rho, A sub rho, draw in here the radius rho equals A. Out to, in the interior solution, is A phi is proportional to rho, so it just is a straight line like this. And then the exterior solution that falls off is 1 over rho, so it decays like this. If we plot similarly the magnetic field on the same chart, the same type of diagram, it's constant interior and 0 outside, just like that. So, although the magnetic field is 0 outside the solenoid, the vector potential is non-zero. And the vector potential appears in the Schrödinger equation. And so the question is that going to affect the quantum mechanics of particles which are outside the solenoid? To make this a little more concrete, we can imagine that the solenoid is like a hard wall that the particles can't get through. So we have a quantum mechanical problem. If I look at it from above, we've got a quantum mechanical problem in which the wave function is equal to 0. It's the boundary conditions on the edge of the solenoid. And we're going to be interested in solving the Schrödinger equation in the exterior region. We don't care what happens in the interior because the particles don't get in there. Okay, so let's think about doing that. Well, from one point of view, you might be tempted to say, in this exterior region, we have a non-zero vector potential. It's true. This is what I just worked out here. But this is just one choice of gauge. Obviously, if you have a zero magnetic field, the possible choice of gauge is just A equals 0, because curl of 0 is 0. So why don't we do a gauge transformation to get rid of this vector potential and end up with A equals 0. And then in the exterior region, we ought to have just the Schrödinger equation for a free particle, and the magnetic field wouldn't make any difference. Well, let's try to do that. So the vector potential we've got is this one here, this phi component. Now let's talk about the exterior region. Is B A squared over 2 times rho times phi hat. Then we multiply numerator and denominator by pi, because then phi A squared B is the magnetic flux inside the solenoid, so it's phi over 2 pi times rho times phi hat. It's 1 over rho. 1 over rho times phi hat. As we say, this vector potential is pure gauge. It can be gauged by gauge transformation. It can be eliminated. That means it must be equal to the gradient of some scalar f. And what is that scalar f? Well, the scalar f is proportional to the azimuthal angle phi. Don't confuse the magnetic flux capital phi with the azimuthal angle phi. If you compute the gradient of phi, just do it in cylindrical coordinates, you'll find it's equal to phi hat divided by rho, which is precisely what we had here. And so the f here, which is of which A is the gradient, to summarize this, we can write the vector potential in the exterior region is actually equal to the gradient of a scalar, which is the flux in the solenoid divided by 2 pi times the azimuthal angle phi. Okay? And you'll recall that when you do a gauge transformation or a wave function, it goes into psi times e to the I q over h bar c times the gauge scalar f. The gauge scalar f is going to be the flux over 2 pi times the azimuthal angle phi. And so the result is, I'm running out of room. So the result is, in this attempt to gauge away the vector potential in the exterior region, what we end up with is a new wave function, which is related to the old wave function by a phase factor that goes like the azimuthal angle. More specifically, it's this. The new wave function, or the transformation is this. It becomes e to the I q over h bar c times the function f is, where did I write it down? Did I write it down? The function f is the flux phi over 2 pi times angle phi. So that's 2 pi h bar c times angle phi, flux capital phi times angle phi. Q over 2 pi h bar c is the same thing as Q over hc, which is 1 over what I'll call phi 0, where phi 0 is the same flux quantum that we saw in the charged particle in the uniform field. So this can be written this way as psi times e to the I capital phi over phi naught times the azimuthal angle phi, like this. Now, trouble is, you see, is that when you go completely around, if phi over phi naught is not an integer, you get discontinuity in phi. Yes?
When we do that gauge transformation, what would happen to the vector potential inside the solenoid? Would that not get changed?
Well, I'm glossing over that because I'm saying, suppose we just want to solve the Schrodinger equation in the exterior region. So I'm supposing let's just try to do a gauge transformation there to get rid of it. If you do that, what you'll find is that the new wave function is related to the old wave function times a factor, which is the flux in the solenoid divided by a flux quantum times the azimuthal angle. Now, if this ratio is not an integer, then the new wave function is discontinuous. That's a problem. If it's discontinuous and the momentum is infinite, you've got problems with that. So let me not go into the problems of the discontinuities of the wave function, but this is a reflection of the fact that it's not going to work to gauge away the vector potential in the exterior region, even though the magnetic field is 0 out there. Another way of saying it is that if I were able to do a gauge transformation to get rid of the vector potential in the exterior region, then obviously the integral, the loop integral of a dot dl would be equal to 0, because if a was equal to 0, this would certainly be equal to 0. But that can't be right, because this integral must be equal to the flux, which is contained in the solenoid. So the result is you cannot gauge away the vector potential in the exterior region. It has to do with topology, really, the fact that there's a hole in the space. That's really what makes the difference about being unable to do this. All right, let me not follow this any further, except just to say that the result of this is that there's a phase shift in effect on going around the solenoid compared to the free particle solutions. And the phase shift is precisely this if I replace this by 2 pi going around the solenoid. The phase shift is this. It's the ratio of the flux to a flux quantum times 2 pi. And what you find is that solutions in the presence of that vector potential compared to solutions, free particle solutions, when there's no vector potential, differ by this phase shift when going around the solenoid. Now, let me show you how this might have an effect physically. It does have an effect physically. This is maybe the most dramatic physical effect, way of describing the effect of this. Let's consider a double slit experiment where we have, let's say, plane waves coming in like this. And there's two holes, and you know what will happen is you get waves radiating from the holes here. And then you've got a screen downstream from this, and as you know, you'll get an interference pattern here. And the crests are the places where the phase difference coming from the two holes is a is an integer multiple of 2 pi, so that the two waves are in phase with one another. Now, let's modify the experiment by putting in a hard-enough-bone solenoid right there behind the screen. This particles never see the solenoid, they never come close to it, they're just passing through the holes. But because of the presence of the solenoid, the solutions in the presence of the solenoid have this extra phase factor, relative phase, when going around the two sides of the solenoid compared to the free particle solutions. And what that means is the relative phase of these two waves shifts by precisely this amount. That is to say, phi divided by the flux quantum phi naught times 2 pi. That's the phase shift, extra phase shift that's induced between these two waves. And so what happens is that the interference pattern moves to the right or the left, depending on the flux in the solenoid. And if we make this time dependent by changing the current in this, we can move this interference pattern back and forth. Now the point of this is that the interference pattern is physically observable. So this is a physical effect which appears in quantum, purely a quantum effect. There's nothing nothing analogous classically, which occurs in a situation in which the charged particles never enter a region where there's a non-zero magnetic field. And so this is what Aharonov and Bohm pointed out in 1961, and some people said, oh, it's no big deal, it's just a solution to the Schrödinger equation. And other people said, oh, this is the greatest thing. So anyway, I think there's still kind of a skitsy attitude about the Aharonov-Bohm effect. But it certainly is interesting, and this is what it predicts. Now, by the way, the Aharonov-Bohm effect has been actually experimentally verified. As usual with Gedanken experiments, the real experiments have to be, for practical reasons, have to be somewhat different. But the Aharonov-Bohm effect has been verified experimentally. So there's no question that this sort of thing actually really does happen. All right.
I'm sorry.
Yes.
Maybe I misunderstood something. When you finished this gauge transformation thing, you said, so this is wrong, and then now you're saying that it's right?
No, what I said was that it's impossible. You see, if it were possible to gauge away the vector potential in the exterior region, then the Schrödinger equation in the exterior region would be that of a free particle,
yeah,
with no effect at all. In which case, the interference pattern would be just what you'd always get for what you've always learned about double slit experiments. But the point is that if I put the solenoid in there and turn it on so I've got a magnetic flux, then there's an extra phase shift between these two waves. So that in computing where the peaks occur, you have to include an extra shift. Now it's a relative shift between the two waves. So it's a relative phase shift. Remember, the phase of the quantum wave, we may like to think there's spherical waves coming out of here. And these spherical waves, of course, the wavefronts are the lines of constant phase. But who defines the phase? It's easy enough if there's no vector potential around. You just say, for A equals 0, it's just these are just spherical waves, where there eats e to the ikr coming out of here, e to the ikr over r. But in the presence of a vector potential, then you have to specify a gauge, and the phase of the wave function depends on the gauge, and it changes if you do a gauge transformation. So what the wavefronts are depends on your phase convention. As weird as it sounds, that's true. But the phases themselves are not measurable. What's measurable are phase differences. And the phase difference between these two routes, even in the presence of the solenoid, depends only on the flux in the solenoid. And the flux in the solenoid depends on D, not on A. So it's a gauge invariant quantity. So what's physically measurable is gauge invariant. So although the vector potential plays a more fundamental role in quantum physics than it does in classical physics, it still remains true that the gauge convention is still just a convention, and that the real physics doesn't depend on that convention. The real physics here is the phase shift, the relative phase shift between the waves, and that depends only on the flux of the solenoid. Well, we're so out of time, I didn't really have time to go into what else I wanted to talk about, which is how this appears in path integral formulation. Let me just say that in the path integral formulation, you have a phase in the path integral. It's e to the I over h bar is the integral over time of the Lagrangian. Let's say t0 to t1. And this is integrated over path space in the x of t. We're doing a path integral. This is the propagator K. And the Lagrangian has two terms. It has a kinetic energy, which is m times x dot, or 2 times x dot squared for the path. And then it has another term, which is q over c times x dot dotted into the vector potential. And we can call this, let's say, L0, which is the free particle contribution of the Lagrangian. Let's call this Lm, which is the magnetic contribution of the Lagrangian. So in comparison with the path integral for a free particle, of course, with the solenoid in the center and a hard wall on it, the particles, in a sense, is only free in the exterior region. And we can accommodate that in the path integral just by taking paths that never enter the forbidden region. So let's understood that here in the path space we integrate over. So then all we've got here is just the free particle Lagrangian plus the magnetic particle Lagrangian. But the magnetic particle Lagrangian, it turns out, is independent of the path is largely independent of the path. Let me show you what I mean by that. Let's say that here's our Harnack-Bohm solenoid. Let's say here's the position x0, here's the position x1, and we've got a path that connects the two of them. And let's define the magnetic action as being the integral along the path of the magnetic contribution to the Lagrangian. Let's call this AM, stands for magnetic, it's a function of the path, x of t, and this is q over c times the integral t0 to t1 of a dotted into the velocity x dot dt. Well, this turns into a line integral. It's q over c, the integral from x0 to x1, or simply a dot dx. And so you see the time parameterization drops out. And the magnetic contribution of the action does not depend on how fast the particle traverses this path. Actually, it depends on even less than that. Because if I have two paths, let's call them P1 and P2, such that they can be continuously deformed into one another, then the magnetic action along these two paths is the same. Because if I go along one path and back along the other, that gives me a loop integral, which is equal to the magnetic flux through the enclosed region. But this is entirely in the exterior region where the magnetic field is zero. So if you stay in the exterior region and you continuously deform one path into another, you don't change the magnetic action. And so the magnetic action for paths of that sort can be taken out of the path integral. Well, not quite, because there are paths for which the magnetic action is not the same. Let's call this P3. These are paths that, relative to the initial path, go around the solenoid. In fact, if we deform this path continuously, we can turn it into this, partially follow P1, and make an excursion over here, go around, come back, and then follow P1 again. So we go backwards and forwards like this. If we do this, then the magnetic action along P3 is equal to the magnetic action along P1 plus Q over C times the flux in the solenoid. And so the result is, in the path integral, you can break paths up into what are called homotopy classes. These are the classes that indicate how many times it goes around the solenoid. And all paths that belong to the same homotopy class give the same magnetic action, and that can actually be taken out of the path integral. Anyway, the result is the path integral becomes a free particle path integral taken over paths belonging to a single homotopy class, multiplied by a phase factor, which is precisely this Harnack-Bohm phase, exactly this here, times an integer. So it becomes P I n phi over phi naught. And this is the phase factor that distinguishes one homotopy class from the other. Anyway, by doing this, it becomes obvious that the propagators in the presence of the solenoid is not the same as it was in the absence of the solenoid. Okay, I think that's all. Just to remind you, there'll be no other class this week, because I'll be out of town. There's a few more homeworks here. I don't know which one this is. Equation, the third eigenvalue equation looks like this now. It becomes, replaces pz by the operator minus I h bar dz. We get an equation like this, minus I h bar dz plus b over c times a sub z, which is a function of x, y, and z, acting on psi is equal to eigenvalue p3 times psi, same psi of x, y, and z. Now, what makes this equation hard to solve is the vector potential component a sub z. And so we ask ourselves, is it possible to choose a gauge? Let's try to choose a gauge now to simplify the equations. Can we choose a gauge such that az is equal to 0? Can that be done? Well, let's write out the equations, the components of b equals del cross a. Take the z component, we have b, which is the same as the z component, is at dy with respect to x minus partial ax with respect to y. Just write out the full equations. 0, which is bx, is equal to partial az with respect to y minus partial ay with respect to z. And 0, which is by, which is the third component, is equal to partial ax with respect to z minus partial ac with respect to x. Just writing out the curl. Now, if az is equal to 0, if we provisionally guess that we can do that, then these two terms here go away. And you can see that what's left is that dy with respect to z is equal to 0, and also dax with respect to z is equal to 0. So these equations imply that ax is a function only of x and y now. And it also, the same is true for ay, is only a function of x and y. That az is equal to 0. This means, as you can see, that the entire vector potential is now independent of z. So a partial of the whole vector potential with respect to z is equal to 0. This means that its vector potential is invariant under translations in the z direction. This is one of the symmetries of the magnetic field. If the magnetic field is uniform in the z direction like this, it obviously has a symmetry, a translational symmetry in the z direction. If you move it up and down, it doesn't change anything. You can also move it to the right and left or backwards and forward, and that doesn't change anything either. The magnetic field has a symmetry, translational symmetry in all three directions. It also has a rotational symmetry about the z-axis. Only about the z-axis, not about the other axes. But anyway, this magnetic field, this uniform magnetic field, has four obvious symmetries. So now one of them is reproducing the vector potential, namely the z translational symmetry. So let's do that. Let's make this assumption. And if we do that, it cleans this up because this term goes away. And also, if we do that, then this term goes away, and we see that P3, the operator, is the same as the PZ operator. So let's just change notation now to the same thing. So let's just take P3 hat and just replace it by PZ, because that's what it is. And likewise, do the same for the eigenvalue. Replace that by PZ. So I'll take this and replace this just by PZ. And so now the equation is easy to solve, and it gives you psi of x, y, and z is equal to e to the I pz times z over h bar times an arbitrary function of x and y. Because there aren't any x and y derivatives here, this is the general solution of that equation. And so the z dependence is determined, and it turns into h perfect to p3. And our strategy then will be to find a set of simultaneous eigenfunctions for those observables. All right. So what we're going to look for then is to solve a set of equations like this. We're going to wave functions can be psi of x, y, and z. And we want, first of all, that x acting on this, the operator, brings out an eigenvalue we'll call x. And you can see I better distinguish the operator from the eigenvalue. So let me use my usual trick of putting hats on any operator where I think there's going to be a confusion between the operator and an eigenvalue or some other C number. So anyway, this is the eigenvalue eigenfunction equation for the operator x hat. Likewise, we'll have H perp acting on the same side. We'll bring out an E perp, perpendicular energy. And we'll have a P3 hat acting on the side. We'll bring out a P3 eigenvalue acting on the side, multiplying side. So these are three simultaneous eigenvalue equations that have to be satisfied. Now, so let's work on these. The H perp is the most complicated of all, and the P3 and X hat are simpler. So let's do the simple ones first. Let's work on P3 hat first. P3 hat is from the formula down here. It's the mass times Vz. And Vz, the velocity, is expressed in terms of the canonical momentum and vector potential by this equation. So we'll put those together. And P3 hat then is equal to the mass times Vz. I'll put a hat on Vz. And that's the same thing as momentum Pz plus E over c times the vector potential Az, which in general depends on x, y, and z. And so this eigenvalue, the last lecture I worked out the energy levels for a charged particle moving in a uniform magnetic field, and I've summarized some of the calculations here on the board. The main result was the energy levels, which depend on two quantum numbers, m, which is a Landau quantum number, and then P3, which is the momentum parallel to the magnetic field. You know, the particle moves as a free particle in that direction. The Landau level corresponds to a harmonic oscillator with energy equal to half h bar omega. Interestingly enough, the Q and the P of the harmonic oscillator are basically the x and y components of the velocity, which don't commute with each other. So the harmonic oscillator itself is really just Vx squared plus Vy squared times m over 2 as the kinetic energy. This is the quantized values of the perpendicular kinetic energy of the particle. In fact, the whole energy is kinetic energy. Anyway, that was the main result of last lecture. And in this lecture, what I'd like to do is to start by working on the not just the energy levels, but also the energy eigenfunctions. So let me start with a clean board here and get to work on that. The strategy is going to be to choose a complete set of commuting observables, a CSCO. For starters, we can take for starters, we may notice that the perpendicular Hamiltonian and the parallel Hamiltonian commute with each other. I'll have to keep lifting this up to show you the summary from last time. But the reason they do is that, you know, there's 3 degrees of freedom. One, which is basically the guiding center position, x and y, the q and the p. The 2 degree of freedom is the x and y components of velocity. And the 3 degree of freedom is the z and pz in the parallel direction. So the reason that h perp and h parallel commute with each other is that h perp only involves number 2 degree of freedom, whereas h parallel involves number 3. So they commute with each other because the commutation relations are qi pj is I h bar delta ij. So their commutators are 0 for different degrees of freedom. So the Hamiltonian is a sum of 2 terms that commute with each other, and so we can take these 2 terms, h perp and h parallel, as being 2 of our members of a complete set of commuting observables. Let's write this set like this. Now, actually, as it turns out, instead of h parallel, it's actually better to use P3, the parallel component of momentum. This is really just a one-dimensional free particle. And the idea here is that momentum is preferable because the energy is degenerate. You know, in a free particle in one dimension, you've got 2 waves traveling in opposite directions have the same energy. That's resolved if you use the momentum as the quantum number. So allow me to do that and replace h parallel just by P3, like this. That gives us 2 commuting observables. But we need another one, and it's pretty clear that we do because the number 1 degree of freedom is not represented by h parallel and h perp. That's the x and y, the guiding center positions. So if we want to find a third observable which commutes with the first 2, it obviously can be any function of q1 and p1. Or for that matter, it could be, call it x and y. It's the same thing apart from these constants. So it's the guiding center position, some function of m. And the simplest choice is just to take it to be x. We can make it y. Let's make it x just to give it a choice. So let's take a complete set of commuting observables, and we'll take it to be x.